All right, today we're going to talk about gravity. All right, if you're following along in your book, this is section 10.3. Okay, now gravity is one of the fundamental forces of nature. It's one of the forces that just exist all the time and everywhere. All right, and the law that states this is the law of universal gravitation. Okay, now if you don't know what that means or don't know what gravity is, hopefully at this point you do. Most people understand that the reason we can stay on the earth without floating off is gravity, right? And why is that? Okay. Well, what the law of universal gravitation states is that any two objects attract each other through gravitational force. Okay. So any two objects, specifically ones that have mass, any two things that have weight, all right, draw each other to each other. Okay. So they draw to each other. All right. Now, that being said, the Earth being an object with weight and you being an object with weight, okay, draw each other to each other. Okay, it sounds weird every time I say it, but most people know the Earth pulls on you, sure. All right, but did you know you also pull the Earth towards yourself? Okay, and obviously this is one of those things that it's kind of trivial because the Earth weighs so much more than you do that the Earth doesn't even feel it. Right? It's like when a tiny bug lands on your arm, you hardly even notice. Right? You're lucky if you notice and you're able to swat it off. Right? So you pull on the Earth pulls on you. Now, put this a little further, okay, I said that any two objects pull on each other. So me and this chalkboard, right, or this whiteboard, all right, are pulling each other towards each other. Now, the problem is that we don't weigh a lot, right, in relative to a cosmic scale, to the Earth's weight, right, we notice the Earth's weight and gravity pulling us down, right, but because me and this board don't weigh anywhere close to the Earth, I mean, I'm getting there, but not quite that far, okay? We don't pull each other with that same kind of force. Not even on a scale even similarly close. Probably millions and millions of times off. Much smaller than the Earth's pull. Alright, and so there is a formula for this. The force that gravity exerts on us, or the force that gravity exerts on any two objects. Alright, and it is right here. So the force exerted by gravity, alright, is equal to G. It's capital G. Notice that? Well, we're going to come back to that here in just a second. All right, and what that is the gravitational constant. All right, that's a number. It's actually 6.673 times 10 to the 11th. 10 to the negative 11th. Sorry, that's page 230 in your book if you need that. All right. Anyway, so force equals the gravitational constant, all right, kind of the number that describes gravity, times the mass of the first object, m1, times m2, that's the mass of the second object, divided by distance squared. Okay, so think about it this way: Jupiter or Mars, right? Actually, don't know about Mars. Jupiter or one of those really, really massive planets is much bigger, all right, but it doesn't pull on you as much as the Earth does, right? You're not getting pulled off the Earth up into Jupiter, right? The reason being is you're so far away from Jupiter that it doesn't really pull on you much at all. All right, so distance matters. How close you are to an object, the closer you are, the harder it's going to be able to pull on you. All right. Also, like I said, the masses of the two objects matter a lot as well. If one object is really, really, really massive, that can create a lot of force and a lot of draw between the two objects. Okay? All right. Now, I said we're going to come back to G. All right. Capital G is the gravitational constant. All right. This number is 6.673 times 10 to the negative 11th. All right. You just plug that in your calculator, use that number. All right. The number has been measured and calculated by scientists. All right. You don't have to worry about that. All right, now, that being said, little g is when we're talking about gravity, all right, so current gravity. Depending on the two objects and depending on where you are and what you are, that's what we're going to talk about as g, all right. G on Earth just happens to be about 9.81. All right, I know we talked about this the other day, but the units, all right, for gravity are meters per second squared. All right, meters per second squared. And we're going to dive into that. All right, so gravity here on Earth, 9.81 meters per second squared. All right, what that means is it accelerates all objects at that exact same speed. 9.81 meters per second every second. Okay, so if you started at 0 and you dropped, right, you jumped off something and you jumped, all right, give a little dude up here. All right, and you jumped. All right, so you started at 0. You weren't moving. All right, after 1 second, you would be traveling 9.81 meters per second. That would be your speed or your velocity. All right. So after 1 second, you'd be going 9.81 meters per second. Now after another second, you would add another 9.81 meters per second of acceleration. All right. So after 2 seconds, you would be going some 9 plus 9 is 18, 8.1, so 19.62. After 2 seconds, you'd be going 19.62 meters per second. All right, if you went another second, you would add another 9.81 meters per second. So every second, an object falling gains 9.81 meters per second of velocity, speed, whichever, if we're talking direction or not. Okay? All right. So, real quick, try that yourself. What would 3 seconds be? If you started from 0 and accelerated for 3 seconds, what does that give you? All right, what would this next value here be? We added 9.81. All right, from 0 to that is 9.81. From 0 to that is another, or from 1 second to 2 seconds is another 9.81. All right, and from 2 to 3, you add another 9.81. All right, so you should come out to something around, let's see, 28, 29, wait, hold up. So 19 should be 28, 29.43. I hope that's right. 29.43, and hopefully that's what you got. All right. All right. Now, this being said, all things accelerate at the same speed, but I just told you that the weight of the object matters. All right, didn't I? So, how does that work? Well, all right, just the same as it's easier to lift this than it is to lift this. Ugh. All right, the same way the Earth is affecting the object. All right, the Earth pulls on that object, and the heavier the object, the more it has to pull. Now, it always pulls at the same speed. It just has to apply more force to move heavy objects. So, for example, I think your book mentions a 2,000 kilogram safe and a 2 kilogram marble. All right, so we have a really heavy safe here. All right, and you have a little bitty marble that you can hardly see there. All right, so the Earth pulls on this safe about 1,000,000 times stronger than it pulls on that marble. All right, but if you drop both those off of a building or off something, they would both move at the same speed. Okay, now I know a lot of you are smart, and you kind of mentioned this in class when we were talking the other day when we did our gravity lab. Okay, but at a certain point, an object will slow down. All right, and that is what is called the terminal velocity. Now, I said slow down. Stop accelerating, I should say. Okay, so when an object is falling, right, eventually the wind that is getting faster and faster and faster as the object falls faster and faster and faster will start pushing the object with enough force to counteract its acceleration due to gravity, right? So, depending on how heavy the object is, obviously the gravity is pulling a lot stronger, so you need a lot more wind to push back up. Okay, so the heavier the object, the faster its terminal velocity. All right, the lighter an object, the lighter its terminal velocity. Okay, so what this means is that the weight of air that is resisting it, the air resistance pushing back up on it, or the drag, all right, is equal to the acceleration due to gravity. At that point, it doesn't accelerate anymore, and it will fall at the same speed, right? It won't be going faster, 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 right? It will fall at a constant speed once it reaches its terminal velocity. Okay? All right. We're going to continue on. Page 232 is where I'm at now, if you're trying to follow along. All right. Solids in circular motion. Okay. So, when an object is moving in a circular motion or circular path, such as a ball on a string being slung around over your head, or the Earth traveling around the sun. Okay, what's happening? All right, is this object is constantly trying to travel in a straight line. Right? If you let go of this object, what does it do? It flies off straight in the distance. Right? It doesn't keep curving around you as it travels outward. Right? It flies off in a straight line. So it turns out that this object is constantly trying to travel in a straight line, but the rope, or whatever is pulling it inward, okay, is preventing it from doing so. All right. So this inward force that is keeping the ball from flying off into the distance, all right, is called centripetal force. All right, centripetal. All right, you should see it there on page 232. Okay, and what that means, it's center-seeking force. It's force that is going towards the center. Okay, now we talked about every action has an equal and opposite reaction. Okay, and so there's a force that is then created that is wanting the ball to travel directly outward. All right, or if you're slinging a ball around, it's the weight that's pulling on your hand, right? You feel it pulling your hand outward, right, as you swing it harder and harder. All right, this is centrifugal force. Okay, centrifugal or center fleeing, right? Fugitive is a term that means fleeing, right? The base of that word. All right, so centrifugal force, all right, is a center fleeing, right? It's like a centrifuge, right? In science, they spin objects around really, really quickly, and it slams them against the walls. That's that center fleeing force. They use that to separate DNA and stuff like that. Or the ride at the fair, was it G-tron or something like that? Right, the little dude that spins around and throws people against the wall, and you get like stuck to the wall. That's centrifugal force that allows something like that. Okay? All right, now, why is this important? All right. Well, if you cut this rope, what happens? Right? If you cut this rope, the ball, at whatever direction, takes off flying in a straight line and is gone forever, wherever it may go. Okay? But very similarly to this, the Earth is traveling in a curved path around the sun. Right? Now, there's no string attaching the Earth to the sun. That had to be a very big, very long, very strong string. Right? But what is there between the Earth and the sun? Well, these are two objects with mass. Right? So we have gravity, right? And a lot of it, okay? So the gravity between the Earth and the sun is enough to keep the Earth from flying off into space in whatever direction it may be currently traveling, okay? So this creates a centripetal force and a centrifugal force between the Earth and the sun, allowing the Earth to travel in an orbit, right? This centripetal force keeps it from flying off into the distance. All right? If all of a sudden gravity wasn't a thing, we would be heading to some outer solar system, and it would not be pretty. We would cool down very quickly, or if we got shot in the wrong direction, we would then warm back up very quickly in another sun. All right. So this is centripetal force and centrifugal force, objects traveling in a circular motion.